Roman numeral 2, and we're going to say here this is vector addition math, vector addition math. So we're actually getting into the math side of vector addition now. Let's get right into an example problem. It's the best way to learn, and we'll keep upping the complexity of the problems as we go. We're going to start with a relatively easy one though. So remember, vector addition can be used for displacement vectors. It can be used for velocity vectors. It can be used for force vectors. This method that you're learning right now can be used for any type of vector quantity. So let's use displacement. That's usually the easiest way to start. We'll say a crying kid in Walmart. It's funny because it's true. They cry everywhere, right? But okay, I'll stop. A crying kid in Walmart runs, let's say, 20 meters north, right? So he's running 20 meters north. Notice I just gave you a vector, didn't I? It's got a magnitude, which is an amount, and a direction. Down, so down an aisle, I guess we could write that down the food aisle. Ooh, I just forgot how to spell aisle. Aren't I embarrassed? That's right, I think, right? Aisle? Okay, food aisle. Then 50 meters, let's go 50 meters. Let's say west. Down, I don't know, it doesn't really matter, right? The clothing aisle. And finally, see, I'm mapping this in my head, north, west. Let's go ahead and let's keep this one relative. Okay, 30 meters south. You can make up the aisle if you want to. I'm just going to say south, right? Leave it there. What is his resultant displacement? Let's find out that resultant displacement. Now again, those of you who can reason this out in your minds probably don't need to do the visualization technique of head to tail addition. Too bad. We all need to do it. Your tests will be graded based on your ability to do head to tail vector addition visually and mathematically. So let's draw a good picture. That's always the first thing you want to do. Actually, maybe even before that, this is up to you. If you don't want to do this, then you don't have to, but I'm going to do it for this first problem. My first displacement, my delta x, because that's displacement, right? 1, my delta x1 is 20 meters north. My delta x2 is 50 meters west, and this just helps you to organize your thoughts. 30 meters south. Okay? Now, we're going to start in our paper somewhere. Now let me explain. It would not be a great idea for me to start here, right? This would be a dumb place for me to start drawing because I have to go which direction first? North, right? So I'm going to run into my words. So usually you can think about how this is all going to work. I also wouldn't want to start here, right? I could go 20 meters north, but then if I go 50 meters west, I run into all my writing. So you want to think about it before you start. I'll put my pen right here. This should work just fine. I'm going to say that's 20 meters north. All right, so, and next to this, I'm actually going to put delta x1. And if you want to put the value here, it's not bad, you can, 20 meters. And then we go 50 meters west. Now, west is to the left. In fact, maybe you need to see a little compass rose off to the side. No big deal. That's north, that's south, left is west, right is east. Like that. So we went 20 meters that way, then we go 50 meters. And this is the other important thing. Do I want to stop my vector there? If I just made basically 2 lines worth is 20 meters, well then I got to go maybe like that far. If that's 20 meters, that could be 50 meters, right? You don't have to be exact, but you should try to draw your vectors relative to one another. I'll say that again. You want to have the vector lengths correct with respect to each other. They have to have the right relative lengths there. That's how you say it, the right relative lengths. If you make that 20, then this baby better be bigger if it's 50, right? And then finally 30 meters south, well, that's easy because I made one space 10, right? So I'm going to go 3 spaces down and make that 30. Notice what I've done every single time. I've labeled my vector, delta x1. I put the value, labeled it, put the value. That's a good idea, and this probably should look more straight up and down. There we go. And notice the other thing. The tail of the next vector and the next vector went on the head of the previous vector, right? I drew the first vector, then the tail went on the head. That tail of the 30 went on the head of the 50, right? And now here's where things are going to be different for the first time. What does our resultant vector look like? You can't just say 20 plus 50 plus 30, wash your hands and say the problem's done. It makes no sense. 20 is going north, 30 is going south, 50 is going west. You can't just add them straight up. You could add them straight up if they were all going west. If you had 20 west, 50 west, and 30 west, they're all going the same direction. Sure enough, you can add them up. But here we have all these different directions. Let's draw in our resultant vector. You start at the tail of the first vector, and you there's my resultant vector. And you'll notice my result is happening at an angle. I've got to find this resultant displacement. I'll call it delta xr, right, for the resultant displacement. Okay, so I showed you the first step. You draw a good picture, you make sure the vectors have the right lengths with respect to each other. Draw or sketch in your resultant vector, going from the tail of the first to the head of the last. Here's your next step for now. If all the vectors, and I'll say this, if vectors are, and I mean these 3 vectors here, if vectors being added are purely in the x and y axis, then components are not needed. Components are not needed. What are components? That'll be in the next example problem. I'll explain what components are not needed. But this is important for you to be able to look back at this example and when you apply it to future homework problems and say, okay, this homework problem is like this one. Are these vectors purely in the x and y axis? Yeah. This one's completely in the y-axis, this one's completely in the x-axis, and this one's completely in the y-axis. Well, what does a vector look like when it's not in the x, not purely in the x and the y? It means it's an angled vector, right? If you had a vector that was acting at an angle, like vector A back in the previous 2 examples, now you're talking about needing these things called components. That's for the next problem. If you don't have that issue though, and you don't, right, all of these are perfectly up and down or left and right, then here's what you're going to do next. Sum up vectors in each axis. You're going to sum up the vectors in each axis. So let's go ahead and see what that looks like. This is a weird looking symbol. It's called sigma, okay? And it's just like that, okay? That means the sum of. It's kind of like net. You could honestly say net here instead. If you like the idea of net, that's fine. Same thing. Sigma, the sum of the delta x's, the displacements in the x-axis. Let's do it. The sum of the displacements in the x-axis. How many of these vectors are acting in the x-axis? Just one. Isn't that it right there? All you have is delta x2. That's the only vector you got, and it's acting in the x-axis. So I'm going to go ahead and right here, 50 meters. That's it. Done. And maybe I should state the direction that it's west. Okay. So I just added up all my x vectors. There's only one x vector. Let's sum up our vectors, our displacements, right? Sum up our displacement vectors in the y-axis. Well, here's where you need to go back to what I taught you in forces. Always lead with your dominant direction. Who's the dominator, south or north? South is dominant, right? So we're going to do 30 meters. We're going to put that first because we don't want to end up with a negative answer. Always start with your dominant direction and start with that one by starting with it, you're saying that's the positive direction. Okay, so 30 meters minus, because 20 is acting the opposite direction, and you get 10 meters which way? 10 meters south. Isn't south winning? South is bigger than north. There you go. And you can see the issue. If I had done 20 minus 30, 20 minus 30, which you can do, but then what you're ending up with here is a negative answer. You'd have 20 minus 30, which would be a negative 10. And there's no need for that. What would the negative mean? It would just mean that it was going south. But instead, let's just always lead with the bigger vector and call that the positive direction. So 10 meters south, enough said. What did we just find? These answers, remember, I know this one is painfully simple for a lot of you. I get that. But if you understand this process, you're going to be able to apply it to harder problems. And trust me, they are going to get more difficult. So these answers we just found, these answers are the x and y component of the resultant vector. Very important that you understand that. I will ask this over and over again in class. Ask it in warm-ups. I want you to understand that once you sum up the x's, the x-axis, and sum up the y's, the y-axis, you just found the x and y component, or the x and y piece. I'll even put that word here, piece. Okay, I misspelled piece. I always mess up with my I's and my E's. I apologize if I did. So the x and y piece of the resultant vector. So what does it mean? This is what I mean. Here's my resultant vector. Yes, there it is. I don't know what value that is. It looks like it's probably a little more than 50. Maybe it's 55 based on these lengths that I have, but I don't know what it is. I need to find it, but no problem. I'm going to redraw this so we don't confuse ourselves right here. I'm going to redraw it right here by using my components first. I go how far south? 10 meters south. And I go how far west? 50 meters west. Notice I'm putting the head to the tail, the head to the tail. I think that's about 50 meters. So there's my 10 meters, there's my 50 meters, head to tail, and now I go from the tail of the first to the head of the last, right? And that's my resultant vector. Oh, I called it delta XR, right? Delta XR, right? There's my resultant vector. Doesn't that look pretty much the same as this one here? Yes, because we just did. And if you prefer to use the original drawing, you could certainly do that. You could say, okay, but people get confused because of these other vectors that are already here. Didn't we just find 10 meters south? Didn't we just find 50 meters west? Isn't this the x, the y and the x piece of this resultant vector? The y and the x, what's the word I'm using? Component of this resultant vector? Yes, it is, right? So I usually redraw my triangle down here with my new answers, right? 10 and 50, and then boom, there's my resultant. Well, some of you, while I've been saying some of the same stuff over and over because I want to make sure that everyone's getting it, right? You already know what to do, right? You've already decided, I know what to do. This is easy. This is a right triangle. This is a squared plus b squared equals c squared. This is Pythagorean theorem. So that's our next step. The answers are, these answers are the x and y component of the resultant vector, right? So I've drawn that. So we could say here, next step would be to draw the components and resultant. want to say the final components, because these are those final components of that result. Then we will do Pythagorean theorem. To find resultant. Okay, let's do it. So I'm going to say here 10 squared plus 50 squared equals delta x r, my resultant displacement, squared. Well, if I want to find the resultant displacement, wouldn't I just take the square root of both sides, like that? And I would end up getting delta x r. And you'll see me do this a lot. I'm not going to do this whole step that you see me do here where I cross the two out. I'm going to go straight to writing what you're seeing right now. In class and in the future, I will go straight to writing this. The square root of a squared plus b squared is the answer. All right, let's get it. Get your calculators, or you can sit there zoning out while I do it. Not a good idea. You should always practice your calculator work. Always, always. And we end up getting 50.99, so I think we can safely say that's 51, right? So this is roughly, pretty closely, 51 meters. 51 meters, and you think, oh, finally, we're at the end of that problem. But we're not. We found, guess what? We just found the magnitude of our final vector. That's the amount. But we also need to find the direction. And this is where things are different than what we've done so far. We cannot easily say, look at this answer here that I have. This is it right here, right? There's the head of my vector. So we're kind of going south and west at the same time. Is it enough to say southwest? No, you can't say southwest, because southwest means at 45 degrees. Southwest would be that, right? Splitting these two axes perfectly. So we can't say southwest. So what's the direction of this vector? Let's find the angle. How do we find the angle? Da-da-da. We got to find this angle theta with trigonometry. Oh no! Yes, trigonometry. Theta, T-H-E-T-A. Theta is a Greek letter, and it looks kind of like this. Theta. It's like the circle with like kind of like a little loop on the top, right? And I use that a lot for angles. So how do we find theta? Well, fear not. We have an adjacent side and an opposite side. So if you remember SOHCAHTOA, which we're going to use in our next lesson a lot, SOHCAH, that's supposed to be an A right there, TOA, SOHCAHTOA, sine is equal to sine of theta, sine of the angle is equal to opposite side over hypotenuse. Cosine of the angle is equal to the adjacent side over the hypotenuse. Tangent of the angle is equal to opposite over adjacent. So if you don't remember this, or you're very rusty at this, which I would say most of you are, don't worry. I'm going to teach you what you need to know about trigonometry in my class to be able to do the problems, all right? We need to use tangent. Here's why. I just found this hypotenuse of the right triangle. There's the right angle. 51, but I already had this side and this side. Do you see how this side is actually touching the angle? This side is physically touching that angle, right? That makes this the adjacent side. That's the adjacent side, right? You see how this side, the 50, is acting opposite, or is opposite from the angle? This is the opposite side. So I just want to make sure you see my arrows there. Okay. So I'm going to use tangent, because tangent uses opposite and adjacent. So right underneath this, I'm going to write tangent of theta is equal to my opposite side, which is 50, over my adjacent side, which is 10. Well, that's pretty cool, because tangent of theta then would equal, it's 50 divided by 10, that's 5, right? So do you remember how to isolate theta now? Do you remember how to find this angle theta? You do the opposite of tangent, which is called inverse tangent. And on your calculator, there is a tan with a -1 button. So if you take the tan -1 of both sides, the tan -1 would cross out that tangent, right? And the tan -1 would stay with the 5. And we call this the inverse tangent, also called the arctangent sometimes. And on your calculator, almost done with this problem, guys. Hang in there. You have second tan, see the little tan with the -1, 5, and you end up getting, there it is, 78.7 roughly, right? 78.7. So my angle theta is 78.7 degrees. Now you think we're done, and we are so close. We are so stinking close. So I'm going to put here at 78.7 degrees. But here's where it's really important. It's either south of west or west of south. Which one is it? And this is a struggle for everybody. So I'm going to explain it right now, and you're going to still need me to re-explain it. So don't feel bad. What is your, here is your result, right? Here's your result. That's delta x. How much was it? 51. If I put a little xy axis here, and that's what you need to do, go to the tail of the result vector. Here's my result vector, right? There's the head of it. There's the tail. Put an xy axis. Where is the angle touching? The angle is touching the south. The angle is not touching west. There's the west. See, that's the west, right? That's the west part of the axis. The angle doesn't touch the west. It touches the south. So we are of south. We are of south. We belong to south because the angle touches the south. And how did you have to swing from south? You had to swing which way? You had to swing to the west. Didn't you have to swing to the west from the south? So west of south is how that's stated. And man, I know that was a long process, guys. These are tedious problems, but the cool thing is it's actually a method that works for any type of vector. Here it was displacement vectors. We'll be using this method for force vectors, for velocity vectors, and we're going to do a lot more examples to get this thing down. Thank you for listening. I'm looking forward to this new quarter with you. Have a good day.